Thank you, Rodica, and thanks everybody for being here. So to give me an opportunity to advertise for an open problem that I hope will make many of you curious. So my title has bridges and nanomechanics in it. So here's a picture of a bridge. I just pulled it from the internet last night. So what do you want from a bridge? I'm sure you don't want that, right? Okay, so you want it to be rigid. Yeah, you want to, when you drive on the bridge, you don't want it to shake. You don't know how long it will shake. Okay, so at the other end of my talk is nanomechanics. Anybody knows what this is? I've seen at least a poster that has something to do with viruses. Is the person in the audience? Yes, so you know what this is? So it's an image of a virus obtained with a technique called cryo-EM. You basically freeze this object. This object is very tiny. You cannot see it with a microscope. It's a little, the limit to the current technology as to how close we can see at the atomic level. But anyway, so this is a cryo-EM picture of a virus. And there are many around these days, and people are very interested in their structure for the following reason, is that for them, in order to function, they have to be flexible. So what you see here is another image of the same virus, and you see that it looks different. And in fact, it needs to be flexible because what it does, it contains the deadly part of it, is the viral DNA. And in order to become viral, it has to release the DNA and inject it in your cells. So this has to be flexible, and we like to understand why. So at one end, we are interested in rigid structures. At the other end, we are interested in flexible structures. At one end, we are interested in big structures like bridges. At the other end, we are interested in structures that we cannot even see, but maybe we can even design, or at least to understand why they are and explain their behavior in mathematical terms. And not the whole behavior, because what I'm going to do in this talk has nothing to do with the particular chemistry of the materials. It has to do only with the geometry. And in particular with the kind of geometry in motion, which bears the name of kinematics. Okay, so let's start from the beginning. The objects we study are the so-called articulated structures. So here's an articulated structure. You see it every day. It's a door. So the door is connected. It's a rigid one, right? It's connected with a hinge from the frame, and that hinge allows a rotation. And that rotation goes only one way. The door has what is called just 1 degree of freedom. You only need to push in one way and it will close or open. Okay, here's another object. It's also an articulated structure. It's made of rigid bodies, and they are interconnected by joints that also locally allow relative motion. So this is now, it's not just an abstract model, it's built, but it's an abstraction of how maybe the human body looks like. And you see that we have a lot of degrees of freedom here. So a degree of freedom allows us to move the elbow, the shoulder, the knees, and so on. So we look at structures, not just that they are rigid or flexible, but when they are flexible, we are interested in how many degrees of freedom are there and how we can control those degrees of freedom to basically design a motion. Okay, so now let's really go to the abstract level. So the simplest kind of articulated structure is what is called the bar and joint framework. There are more complex ones. There are structures like the door is made of rigid bodies connected by rotatable joints. So it's a whole variety out there. So let's just talk for today just about the bar and joint frameworks. And what I mean is that I have bars that behave rigidly, and they allow rotation around the joint that connects them. Yeah, so this can move. Okay. So when you connect such things together, we obtain a graph. So graph has vertices, yeah, so these are the vertices correspond to the joints. yes? And it has edges, so there is an abstract structure. The abstract structure occasionally depends on what field you are in. It's called the topology of the network. It's basically the connectivity of it, and it's captured by a graph. And if you work with more complex frameworks, more complex articulated structures, there may be different types of more complicated graphs having multi-edges and so on. But for the time being, let's just deal with this very simple structure. So that's the combinatorial part, is the graph underlying everything. And that is ultimately what we like to understand. Which types of graphs produce rigid structures? Which ones produce flexible structures? Can we predict this ahead of time? And why that? Because if we don't do that, we have to rely on very complex calculations that involve algebraic or linear algebra calculations. That would work well for small structures, but definitely not for the ones that we encounter at the nano level that have thousands, hundreds of thousands, millions of elements in them. So that's one of the goals. Okay, so given such a graph, we have the edges, and we want to view the edges as being rigid bars and the vertices as being these joints that allow rotation. So the framework is not just the graph, but it's also a placement in some dimension. So for instance, here, I put, a placement is basically a mapping of the vertices to R to the D. So I can place my framework in the plane, in 3D, and in mathematics, in D-dimensional space. Who prevents us from working in 10-dimensional space? Nobody. We like to understand that. So as we do the placement, we retain the edge length, we store them, and we are interested in structures that have the same edge lengths. So for instance, this one is a placement. This is another placement of the same framework. They have the same edge length. And you can tell by the fact that there are two different placements that something is going on. Yeah? In physical terms, in the physical literature, they refer to this as a phase transition. Okay, so why do we study bar and joint frameworks? Of course, because we want to understand rigidity of the structure. So of course, the rigid such framework is one that does not deform, right? So now, for this one, if I were to build this in the plane, you don't need high-level mathematics to discover that this one is rigid. Anybody sees why this is rigid? So it's a collection of rigid bars, so meaning that I know the length of these edges, and it's made of triangles. And if I have a triangle and I know all the three sides, yes, all I can do is move it rigidly in the plane. I don't change its shape. Yeah? And now I have a collection of triangles, so it's very elementary that this one is rigid. But when they are not connected in this nice fashion, how do we tell? Okay, so the other part of reason for studying such mechanisms, such structures, is for their flexibility. So a transmission mechanism must be flexible. And here I'm showing you an animation of a very famous one called the Poisselier linkage. It was cooked up by an engineer, a French engineer in the 19th century, and it's one that converts circular motion to linear motion. So you see, this end rotates and this end goes along a straight line. It's a very, very famous one. Okay, so this one is very special, but in general, what I want is a structure that is flexible. So my graph has not just several embeddings, but it has a continuum of placements near the position that I started from. Okay, so that's the main topic of the main underlying theme of my talk is rigid versus flexible frameworks. And the rigid ones traditionally are the part of statics, when you build structures that have to be rigid and sometimes overly rigid, very robust. And the other end of the line is kinematics. We want to understand when structures are flexible and how they move and how to design their motions. So statics and kinematics, okay. they flourished in the 19th century at the peak of the Industrial Revolution. So what you see here is, this is about the time when the Eiffel Tower in Paris was built. And at about the same time, in England, we have this very famous physicist, James Clerk Maxwell. And most of the physicists, of course, know about him because he has made some very important equations. The equations of Maxwell, and Einstein's theory is inspired in some sense from Maxwell's equations. But what is less known about Maxwell is that he has 2 geometry papers. Yeah? It's not they are purely geometric, but parts of them are purely geometric. And I'm going to talk, and that's the title of my talk, is the legacy of these 2 papers. Okay? So let's start with the first one. 1864. On the calculation of equilibrium and stiffness of frames. Stiffness in the language of 19th century is what we call rigid today, and frames is what we call frameworks, but it's more or less very readable paper. And I pulled out a little piece from that paper just to emphasize some numbers there. So there is a 3 and minus 6 there, and a 2 and minus 3 here, and then, yeah, well, it's an S there. I'm calling it N in the modern terminology. So this one has to do with the fact that in order to build a rigid structure in 3D, bar and joint rigid structure in 3D, you need to have at least 3 and minus 6 bars. If you want to do it in 2D, you need at least 2 and minus 3, where n is the number of vertices, 2 and minus 3. And in 1 dimension, in order for you a structure lying on the line to be rigid, you need at least n minus 1 bars. Okay? So this collection of triangles, if you do the calculations, if you have a bunch of triangles connected this way, a triangle is exactly 3 vertices, 3 edges, satisfies 2 and minus 3, and so on. Collection of triangles satisfies this. But not only this, there are other structures that satisfy it, and we want to understand in what way. Anybody has a guess where the n minus 2 comes in 1 dimension? Again, I was attending some of your talks yesterday, so I know people know about trees. A tree is a graph, and a graph with n vertices and exactly n minus 1 edges. And if you want to have something that is rigid on the line, it has to be connected. So in other words, it has to be at least a tree. So that's where these numbers come. So they are very, they have very combinatorial meaning. So let's formulate them. So here are Maxwell's conditions in a modern formulation. So I'm doing the formalism in arbitrary dimension, and I define something that is called sparse with a combination here of indices of numbers, or let's call it Maxwell sparse in dimension D. So we have a graph. The graph has n vertices, and let E be the number of edges, and we say that this graph is D n minus D plus 1 choose 2 sparse, or Maxwell sparse in dimension D, if it has exactly that many edges, and on any subset of vertices, so n prime less than n, every subset of n prime vertices spans at most the same formula. You see dn prime minus d plus 1 choose 2. Okay? So let's go to Maxwell's conditions. So in dimension 3, these numbers are, D is 3, because we live in 3 dimensions. This is 2 here, because these are frameworks in dimension 2. And this is 1 here, because it's in dimension 1. So that's this dn here. Okay? And d plus 1 choose 2 is 6 in dimension 3, 3 in dimension 2, 1 in dimension 1, and this is the d plus 1 choose 2. Okay? And anybody has a guess or has encountered this before? Anybody has a guess of where this might come from? It's okay if you don't, I'll tell you anyway. So let's see where these numbers come from. Okay, so let's try to formulate the problem mathematically. So we are given a graph, and we are given a placement of it, and we like to understand whether this is rigid. Okay, so what can we do? So, okay, we have the length of the bars. So why don't we write some equations to say that this particular bar has to have that length? And let's make a system of equations with unknowns being all the possible positions. Yeah? And if we have too many, maybe it's not rigid. Yeah, so let's formalize this. So I'm going to have dn variables, d per vertex. D is the dimension. So if I'm in dimension 2, I have 2n variables. And I have one equation per bar. And the equation basically, so I'm writing it here in dimension 2. So the equation is the bar length condition. So it's the length, this is the Euclidean norm. So the length of the edge has to be a certain constant that I take from my placement. Okay, so that's an equation. So I have E equations. Well, so these equations determine the vertex positions, but only up to rigid transformations in the plane. No matter how many edges I will put, I cannot get rid of the fact that I can rigidly move the object in whatever ambient space I'm in. So that's where this d plus 1 choose 2 comes from. It's the dimension of the space of rigid transformations. And therefore, we need at least that many equations to get to roots that are isolated. It's not guaranteed, but we need at least that many. Okay? So that's where Maxwell's numbers come from. Any questions? Okay. So let me fix a little bit of terminology. What I'm talking about now is part of an area called rigidity theory. And if you go and read the literature, you will be hit very soon with a bunch of definitions. So instead of writing them and losing all of you, I'm going to define the concepts just visually. And you understand what they are. Yes, this is flexible. I just showed you that it flexes, it moves. This one, 2 triangles, is rigid. But I'm going to introduce a new piece of terminology. I'm going to call it minimally rigid, because it's rigid, but not only that, if you remove any of the edges, it becomes flexible. Yeah, so if I remove this edge, it's flexible. Yeah? So this one is minimally rigid. If I put another edge to it, I obtain something that is still rigid. You know, if you have something rigid and you start bracing it further and further, it remains rigid. But then it's redundant. And redundant means that it remains rigid even after you remove some edges. And by the way, that's what we want for our bridges, to be not just minimally rigid, we want them to be redundantly rigid. That's what we want for our buildings, yes? So it's very important. Okay, so if it is rigid, distinguish between minimally rigid, and Maxwell's conditions apply. Maxwell's conditions say something about a number that applies to be minimally rigid. That's what we want to understand. Now, what about when it's not rigid? It's flexible. But when it's flexible, some parts of the structure may still be rigid. Yeah? So in this case, I color code it. So this triangle here, it's a rigid part of my structure. This is another rigid part. This bar here is rigid. This bar here is rigid. So what I did a decomposition. I did a decomposition of the structure of the flexible object into rigid components. Okay, so that's a 1-minute introduction to rigidity theory. And all of this can be formulated algebraically, can be very rigorously formulated mathematically. And here's what we need, right? So we need to define a graph. We need to place it. We need to define what a deformation is. And I'm just illustrating it for you. So I'm just illustrating a deformation. But the deformation is a trajectory. It's an algebraic curve if you formulate it properly, mathematically. And it's an algebraic curve, so therefore you can take the tangent space. And that's where you get the infinitesimal part, which tells you at the infinitesimal level where it's about to move. So if you study this kind of things, you have to understand quickly all these definitions. Yeah. So what is a graph? What is a framework? What is a deformation? What is the realization space? The set of all the possible placements for that particular edge length. What is the configuration space? You factor out the rigid transformation. What is the deformation space? You look at the component of the configuration space that contains your particular framework. You take the tangent space, you look at it's an algebraic variety. The algebraic variety can be smooth or can have singularities in certain parts, and these are particularly relevant. So therefore, you can talk about the dimension of your space, and all these have their counterpart in the intuitive terms. That's how we define rigid, flexible, over-constrained frameworks. We talk about the rigidity matrix, infinitesimal deformations, and also about infinitesimal dependencies or stress. And I just don't have the time to go over all these definitions, but I hope I make you curious and go and read them. And based on this, we define degrees of freedom, like the door that has 1 degree of freedom, my arm that has 2 or more degrees of freedom. There is a certain concept of degree of dependency, and that is the concept of stress that, as we will see towards the end of my talk, appears in Maxwell's paper from 1870 and has very beautiful consequences. So to study all this, you learn a little bit of combinatorics, especially graph theory. If you want to go deeper, you get into something called matroid theory. You need some concepts of real algebraic geometry just to understand that your definitions are robust, especially if you go beyond bar and joint. If we look at other formulations, we need linear algebra because we live in the tangent space and study things infinitesimally. We may need even linear programming, things like Farkas lemma from linear programming for whoever has ever encountered that. But in short, for the purpose of this talk, I'm going to stick to just the intuitive side of it and talk about graphs and frameworks and their deformations. So here's a typical question. We have seen from Maxwell's paper that this kind of sparsity for the graph is a necessary combinatorial condition for minimal rigidity of bar and joint frameworks. And I put here this mysterious word, which is in generic placements. So this means that for most of the cases, except for a measure 0 set of placements, the graph characterization will tell you exactly whether this is rigid or not. Yeah, we need a little bit of algebraic geometry to understand this genericity placement, but for the time being, let's just stick to the combinatorial part. So the main question here, is this condition sufficient? So that's a typical question. So, and you can extend it from bar and joint to body bar to all sorts of other constraints that you encounter nowadays in modern software, for instance, for computer-aided design. People design complex mechanical structures with all sorts of other constraints that can be expressed algebraically besides the bar length. But the bar lengths remain the most challenging part. Okay, so here's the typical answer. The answer is yes, in dimension 1 and 2. Yeah, if you are willing to live in dimension 1 and 2, yes. And the answer was given about 100 years after Maxwell, so it was given in 1970 by a Dutch engineer, Lamont. And it's referred to this as a Lamont theorem. And it says that a graph is minimally rigid in dimension 2. In other words, it's the graph of a framework that is most of the time minimally rigid, if and only if it satisfies Maxwell's condition to be 2n-3 sparse. Yeah, satisfies Maxwell's condition for dimension 2. So that's the typical answer for most of the questions in rigidity theory, is that dimension 1 and 2 are very well understood. But as soon as you go to dimension 3 and higher, it's open. Okay, so the answer is sometimes plain no. And in dimension 3, in fact, there is this very famous example. It's called the double banana. I mean, I hope you can visualize it, right? So it's a tetrahedron on top of another tetrahedron, and they make a banana. Yeah? And that's another banana here. And they're connected at two vertices. So it's obvious that they make a hinge. Yeah? So it's very much like the door in its frame. So if you do the calculations, it satisfies Maxwell's conditions, 3n minus 6, but it's obviously flexible. So which means that we need something else. Yeah? So that's what is called Maxwell's problem. Okay? So it's a long-standing open problem. In the mid-1980s, people were saying, oh, the solution to this problem is around the corner. And it's been around the corner for over 30, 40 years, and it's still not solved. But there's been a lot of activity in the last 20 years. So their problem is characterize the graphs of generic rigid bar and joint frameworks in dimension 3 and higher. Okay, so that's Maxwell's problem. And originally, it originates essentially in the paper that I mentioned earlier. So now let's see, why is it important? And why is it important now, after 150 years? Why are we focusing on it now? Okay, so I'm not going to tell you who Johannes Kepler was, because I assume you know. And if you know, you Google it immediately. And definitely, it's a quote worth remembering, that where there is matter, there is geometry. It's not just building bridges. We are looking at matter. And matter in this sense, so in the sense of the second subtitle of my talk, nanomechanics. So what you see here is a DNA tetrahedral scaffold. And people are building these things nowadays. With DNA, you can design structures. Not only at the macro level, we could do design at the nano level. And we like to understand when they are rigid, when they are flexible, because of the various properties that these different structures have. So, and why that? Because we can model molecules as frameworks. So here's a very simple molecule. So the atoms, we can treat at a certain scale. We are not doing at the scale where we take into account vibrations, but at a certain scale, at the nanoscale, we can assume that there is a fixed bond length between these atoms. So the bond fixes the length. And the angle between the atoms, between the adjacent atoms, is also fixed. So now, this behaves like a bar, and this angle here, if I think of putting here an imaginary bar between this, I achieve the same effect as fixing the angle. So basically, I can convert a molecule into a framework. And I can ask, is it rigid, is it flexible, and can we explain some of its behavior because of these properties? So, I became interested in this problem many years ago, and I wanted to study this because it's essentially about Maxwell's problem in dimension 3. And everything would stop here, given that we don't have a complete answer to Maxwell. So what happens is that physicists are not afraid of conjecturing that this will suffice for the real world. So people have implemented an approximation characterization based on Maxwell's counts and applied it to large molecular structures. So I was intrigued and interested in whether this can be, to what classes actually you can guarantee that that software is correct. And in order to guarantee that, actually we implemented cases where we know that there is an equivalent of Maxwell's theorem that would guarantee that the calculations are correct. So if you are curious, you can go to this site. But what you see here is a software that takes a very large molecule. This is a protein. It's one of the smallest ones, just a few thousand atoms. And what it does, it's basically what you do. I'm illustrating it in dimension 2. In dimension 2, we have a flexible framework here, and I decompose it using different colors into pieces that are rigid. It's the same thing that I'm doing in 3D. So we decompose this big structure into pieces that behave rigidly. Although the whole molecule is flexible, we can tell which parts tend to move as a whole rigid blob. And why is this relevant? Because people study the mechanics and the flexibility of large structures, like this viral capsid that I've shown you in the beginning. And these are huge structures, huge, hundreds of thousands. The largest one was deposited in the protein data bank 3 years ago, and it contains 4 million atoms. It's humongous. And you cannot study the flexibility of these structures at the atom level with classical methods. So you want to make use of this information brought to you by other experiments and try to use the fact that these pieces here behave like rigid pieces. So maybe we can understand this better and with the current technology. So for this purpose, for instance, here's a model of the viral capsid. This is built by an engineer who said, okay, I suspect that from the images, I conjecture that it behaves just as this physical metal body and bar model would behave. Okay, so let me summarize why it's important. So biomolecular mobility is extremely difficult to observe at the atomic level. And why that? Because no computer can handle the complexities of simulating the mobility of such large structures. Even purposely built computers, even if we do molecular dynamics, which is a much higher level simplification than the n-body problem that was in somebody's talk yesterday, even then, there is a huge number of degrees of freedom. And if we compute the rigid components, we dramatically reduce the dimensionality of the problem, dramatically, to the level that it becomes tractable. So when you have a combinatorial characterization like Maxwell's theorem or the equivalent of that, this usually leads to very good combinatorial algorithms. You don't need to use algebraic solvers. You don't need to use linear algebra to do numerical simulation. You can predict from a combinatorial algorithm what are the rigid parts. And then you pass them on to the simulator to do the calculations on a much more simplified structure. So that's the reason that all this is important and came back to life. Okay, so let's now go to the mathematics. I told you that the answer to Maxwell's problem is not known. It's not that we are not actively working on it. And it's known in some special cases, and there have been some amazing breakthroughs in the last couple of years, including something called the molecular conjecture. But I don't have time to talk about all of this. So let's phrase it in more general terms, because I want to show you that sometimes by making the problem a little bit more general, it looks like we are making it more complicated, but in fact, sometimes you can give an answer. And not only that, I'm going to make it more general so that maybe it becomes feasible. And not only that, it becomes feasible, but it has other applications. So in fact, we didn't start this way. We didn't start by generalizing it for the sake of generalization. We generalize it because some biophysicists, some material scientists actually asked a related question to us. So I'm going to generalize it to what is called periodic frameworks. So crystal materials. So here's an example. Until now, we talked about finite graphs. So here's the graph of a crystal, very famous one. The Nobel Prize was given to it a few years ago for various applications. This is a 2D crystal graphene. Graphene comes in layers. It has many amazing properties. It's the tip of your pencil is graphene. Also in dimension 3, crystallographers have long seen this phenomenon. They know that some crystals, very widely known, appear in two what are called phases. So they have the same bond network structure, the same graph, the same edge length, but they are in different placements, in different atom positions. So we call this a displacement. So what they talk about these displacive phase transitions in crystalline matter. And, well, it exists. Try to explain it. Yeah, so that's the problem. And always mathematics is the tool that you want to resort to. And sometimes you simplify the problem. In this case, we ignore the forces, but we are not the only ones. I'm showing you here a page from a paper by the famous American chemist, Linus Pauling. And this is a paper from 1930, where he already observed that the framework, this is really talking in this language, this is a framework of a certain crystal called sodalite. It says, while it is strong, it is not rigid. So he already observed that this framework has flexibility. And it says that the framework collapses, yes, like our bridges that collapse. Well, it collapses up to a point. And as it collapses, it reduces the edge of the unit cell. So the periodicity, the unit cell, the crystallographic unit, is getting smaller. So let me show you an animation on a different crystal, how this might look like. Yeah? So you see that the crystal, that's another one, it's called, this is the sodalite. So it collapses. Okay, so now, what are we interested in? So now I present to you an abstract periodic framework like this, and what do I want to know? Well, is it rigid? Is it flexible? Yeah. So, well, you can, the standard approach nowadays is simulate it. Yeah. So, okay, maybe you do a simulation and you find that it's flexible. If it's flexible, okay, how many degrees of freedom? What are the parts that move rigidly? So by now these questions, I hope I convince you that they are relevant. So we would like to answer these things. And the amazing thing is that we have an answer for this. And this is a recent theorem of myself with Ciprian Borcea. And we have a type of characterization that is in exactly Maxwell style. And it is about a multigraph that we associate to the crystal, to the periodic structure. So I'll tell you in a moment what that is. And the characterization is also with a count, slightly different from the one in the finite case. And also it's done in terms of something called the quotient graph. So we presented an infinite graph, but the characterization, in order to be good and feasible and applicable for a computer to use it, we need a finite characterization of the object, a finite presentation of the object, and that's what the quotient graph will stand for. And the characterization, it's exactly a sparsity type characterization, very much in the Maxwell-Lamont style. However, there is something hidden behind it. And what is hidden behind it is that we use a stronger notion of genericity than in the classical Maxwell situation. Because if we had not used that, we would have solved Maxwell's problem for the finite case. And I told you that we have not. Okay? So I wanted to show you that even problems that are quite easy to state, just in terms of some counts and various other things like this, they may require very sophisticated knowledge from a wide variety of fields. And in particular, this is a question of algebraic geometry, but the algebraic geometry combined with some combinatorial thinking. Yes? So all of these pieces of mathematics come together that allow us to say that we have a theorem like this, but the genericity condition is that measure zero number of situations, set of situations where the theorem does not hold. Yeah? Does it ring a bell? You heard yesterday for the invited talk, it was a similar behavior. Yes, in most of the cases, so with probability 1, the theorem holds, but with probability 0, it will fail. But it doesn't mean that there are not examples. There are sporadic examples. There are infinitely many examples. In fact, there is a continuum of examples, but it's a measure zero set of examples where this theorem fails. And so we are better off because we can confidently apply it to molecules, for instance, because anyway, the coordinates are never quite precise, so we can safely assume that they are generic. Okay? So let's continue. I want to give you an introduction to what went behind developing such a theorem. Okay, so here I emphasized a few things. I emphasized that we are talking about minimally rigid, and that I need to define what is a quotient graph. So let's do the entire line of thought that leads to such a theorem. And the first challenge here is to come up with a good definition. So in fact, that is what that is how we started. So we had this. We went to a workshop, a conference, very much like this, and there was this engineer from Cambridge University that had worked on such structures, and he made Maxwell type of calculations, and something went wrong. So he had a paper where he pointed to this paradox, and I'm not going to tell you what the paradox is, but it really got us intrigued. So the paradox was that if you did a count in one way, you get a number. If you did a count in another way, you get another number. What is going on? Which one is correct? Why isn't Maxwell holding for this? And so then we realized that something actually is fishy here. Everybody thought, okay, so you talk about periodic structures. So, well, periodic usually for a mathematician means why don't we put it on the torus? Yeah, so we talk about something finite. And as you'll see, in fact, that was the bad thing to do. So we prefer to stay in this setting because it allowed us to do something that on the torus you couldn't do. So if you stay on the torus, you keep the space fixed. People talk nowadays about rigidity on the fixed torus. So what we did, actually, we allowed the lattice to move, so we lived on a flexible torus. So let's see. Now, let's go over the definitions. So first of all, let me tell you why this is challenging. So here's the simplest periodic structure that you can imagine. Imagine this infinite, right? So it covers the whole plane. We are in 2D. And you can see that I can deform a whole column simultaneously, and it will look like this. But I can take another column and another one and the row, and basically I have an infinity of deformations. So the space of deformations in this case is in fact, yes, it's an infinite, a countable number of degrees of freedom. It's a countable object. Oh, how do I deal with that on the computer? Yeah? Not good. Yeah. Not only is, I mean, for a mathematician is good, and in fact there are very interesting questions to be answered about the general flexibility of such structures. I don't know yet many results of this nature. So it's an open area for studying for new problems, and many of them are doable. So it's not a good definition because it does not allow for a finite treatment. Rodica told you that I am in a computer science department, so one thing that I can implement. I cannot implement a countable set of things. I need to work at least to search in a decently sized finite space. So we want a definition that is good. So in particular, we notice that these deformations actually do not preserve periodicity. But we have seen crystals, like the one in Pauling's paper from 1930 and many of the existing ones, that when they undergo these transitions, when they undergo the deformations, the periodicity group is preserved. So why not focus on just those deformations that preserve periodicity? Okay, so this is our definition. Again, informally, I'll give you a more formal one in a moment. So we are going to study periodic structures of a periodic structure of rigid bars connected by joints, and it will be constrained to move in a way that preserves the periodicity group. And with this definition, it's a slight specialization of the general setting. This definition turns things from quite intractable to something where you can do meaningful things and practical, with practical implications. So here it is. So I have this structure, and instead of thinking of it as an infinite graph, I'm going to fix one periodicity. Is not unique. Yes, it's not, I can do this in several ways. I can fix the periodicity lattice. And now I allow it. I'm asking, is it rigid or flexible, but not in general. I'm asking, is it rigid or flexible in a way that it maintains the periodicity? It doesn't mean that the lattice is fixed. The lattice may change. The lengths and the angles of the unit cell may change, but the whole thing preserves the abstract group of periodicity. So here, in other words, what we are working with is the following. It's a periodic graph. It's now not just an infinite graph that has some periodicity, but we specify the group. So for instance, if I specify this group, it means that all the points with a similar color are in the same equivalence class, in the same orbit in group theoretical terms. So if I think about the action of a subgroup of this, I consider equivalent only these vertices, and that's a subset of the previous one. Yeah? So it's very important to specify the periodicity group, because that's where the paradox of the engineer came. When you work with different groups, different periodicity groups, the counts are different, and they may give you different results. That's where you get the paradoxes. So that's when we have this. Now we associate the finite quotient graph. The quotient graph is the orbit graph. So basically, each equivalence class of vertices that are connected by periodicity, by action of the group, I put a vertex in another graph, and I retain representative of vertices and representative of edges, and this time I obtain a multigraph. Yeah? So our characterization will be in terms of this multigraph. And this multigraph is a little special, but since we are towards the end of my lecture, I'm going to skip now a few slides that are technical, because I want to get to something that will wake up even those that got lost at this point. So let me skip these things. Okay. So just leave here some pictures to remind you that it's very important that we specify the periodicity. So this is the same underlying infinite graph, but if I take a sublattice, the behavior might be different. And in other words, our periodic graph is the infinite graph together with the action of a certain group, and of course together with the placement both for the vertices and for the periods, for the generators of the periodicity group. So with this now, you can at least understand what is the meaning of this theorem. The theorem says that if I look on this quotient graph, just the graph abstractly, it is the quotient graph of some minimally rigid periodic bar and joint framework, and ignore the other details. I don't have time to explain everything. If and only if it contains a sparse subgraph with d and minus d periodicity in the sense of sparsity, Maxwell sparsity that I mentioned in the beginning. Okay, so that's their characterization. So in the remaining time, I want to tell you how when you start along a path and that path was not anticipated, I would have never, ever thought in my life that I'm going to work on such applied problems. I'm working on them for a single reason, that they have geometry in them. So I've chosen my problems because of the challenging mathematical and geometric questions. And these are problems that could not have been asked in the 19th century because there were no computers at the time. We had to wait for them to be developed. And so now we are going back to those objects. We are going to new applications, larger scale applications, and we are asking new questions. And the questions are often of an algorithmic nature. So we'd like to not just give a theorem, we'd like to give a good algorithm. We like to be able to design tools that will help material scientists or biologists. And for this, we develop new mathematics. So this application came unexpectedly. So let me tell you what it is. And by the way, I put this at the bottom because I hope to get the last 2 minutes of my talk to get to tell you about Maxwell's second theorem. And Maxwell's second paper. So the first paper, I extracted from the first paper a problem, and I told you until now that the problem is not yet solved. But Maxwell has a second paper, geometric paper in 1870 that contains a beautiful theorem. And that theorem, you dig it up from a long time ago, and you have to generalize it, and unexpectedly, it allows you to do proofs. Okay, so that's the moral of the story, and the thread of my talk is that mathematics is alive, even if it was proven 100 and something years ago, and that problems that are long-standing are good and sometimes can be solved, not just Fermat theorem. Yeah. Okay, so let me show you this. So it's something called auxetic behavior. So the auxetic behavior, it's a concept from elasticity theory. Let's make it clear. I never worked in elasticity theory. Okay, I don't know what it is. So, but I saw the definition, and the definition is in terms of something called negative Poisson's ratio. Okay, so people they take their crystals, their minerals, their materials, they measure it, and they come up with a number. But there is no explanation of why the material has this, it's a very counterintuitive behavior. So here's the intuitive definition of what auxetic is you have a material, and okay, here's my material. Okay, here it is. Yeah. So if I pull in one direction, it becomes thinner. Yes? That's what you expect. Do it, try it with anything. So the auxetic material has the opposite, very counterintuitive behavior. I pull, and it becomes larger. So let me show it with a demo. So the demo is prepared by material scientists who work on this topic. So this is a material that has this non-auxetic behavior. And here's a proposed model for why it behaves like this. So if it was a crystal, yes, so you pull and it becomes thinner. Okay? And here's one that has the auxetic behavior. It pulls, and you'll see that it does not become thinner. It enlarges a little bit, not too much. It's not going to pop up like Hoberman sphere. But let's watch. You definitely can see that it's not getting thinner. Yeah? Okay. And now look at the network, the framework behind it. You see, in fact, it's the same graph, but with a slightly different placement. Okay? So what is going on? Right? Aren't you curious? Yeah? Okay, so here's the state of the art in auxetics. So in the 80s, actually 1970, I mean, they are known for over 100 years. It's known that such materials exist. But the first man-made material is basically based on this kind of structure, was proposed in the 1975 or so by material scientists. And essentially, all the examples in the literature are extensions of this, slight extensions. So I can count on my two hands the number of examples that exist. So as an unexpected outcome of our theory, now we have an infinite class of auxetic designs, and I was asking Henry, maybe we can build them, yeah? And until a few months ago, we had this infinite class in dimension 2. I'll tell you in a moment what it is. And I was telling Henry that just less than a few days ago, we put on archival paper where we have an infinite class for three-dimensional structures. Yeah, so we submitted it relatively recently. And that's an unexpected consequence of developing a good definition and a good mathematical theory. So let me tell you more about this. So first of all, I talked about frameworks, but I didn't tell you a good mathematical definition of auxetics, because the one with Poisson's ratio, it means you build a material, try it. that's not good. We like to have a definition that we can test easily. So here's our definition. So the definition appeared a few months ago. So, and the definition is, moreover, it's not about the material, because you see, it's not a property of the material. I pull in this direction and it has or doesn't have, but I may pull in another direction. So it's not a property of the material, it's a property of a particular trajectory that is auxetic or not. So first of all, we have to clarify this. So a one-parameter deformation is auxetic, and this is the definition is the linear operator that takes the period lattice from time t2 to time t1. It has to be a contraction. Simple mathematical definition. I'm not going to go now in details, but I want to tell you that we have this theorem that the one-parameter deformation is an auxetic path if and only if the curve given by the Gram matrices of a basis of periods has all velocity vectors, the tangents in the positive semi-definite cone. Yeah, and again, from your talks, I know some people are interested in these things. So this is very much analogous to the causal lines in special relativity. Yes, so where the curves have all their tangents in the light cone. And in fact, this is not an accident. In fact, in dimension 2, it's exactly relativity. So it's 2 by 2 symmetric matrices form a three-dimensional Minkowski space with their quadratic form, the determinant. And for the dimension 2 auxetic trajectories have associated curves of Gram matrix, which are exactly curved lines in this Minkowski space. So I'm pulling, yeah, you know, I'm telling you how unexpected connections appear. And so let me skip this because I don't have time. I just want to get to the conclusion. So there is a special case of auxeticity that is called an expansive deformation, where all the pairwise distances between the joints increase simultaneously. So it's here that we are getting closer to Maxwell's second paper. I still want to have a minute to tell you about that. Yeah? So here's an example of this expansive structure. So it's a periodic one, and I'm going to deform it. And you pick your favorite pair of points and look how the distance behaves. And I'm claiming that any pair of distances in this framework, as it opens, every pair either stays the same, usually if there is a bar, or increases. It's not that somewhere it increases, somewhere it decreases, like would be in this kind of material, yes? Some increase is. So this is what an expansive structure is, okay? So we have this very simple observation that auxetic implies, expansive implies auxetic. The reverse is not true. Auxetic is its richer concept. But this one gives us now an infinite set of possibilities, because here's how I design auxetics. I design by basically sort of randomly throwing in edges and maintaining just two properties, that these edges don't cross and that I never form an angle, every vertex has all the edges adjacent to it in a half space, in a half plane. So these are the two properties, and this is because we have a full characterization of periodic 1 degree of freedom frameworks, and this is combinatorics, yeah? We jump from relativity, algebraic geometry, and now to back to combinatorics. And the combinatorics is that periodic expansive 1 degree of freedom mechanisms are essentially periodic pointed pseudo-triangulations. And the pseudo-triangulation is, you know, it's this object which is a tiling of the plane with objects that have exactly three corners, three vertices that are convex, that are not larger than pi. And with this, I want to tell you just that this is a highly non-trivial theorem. And in order to prove it, we had to prove along the way a generalization of Maxwell's theorem from his 1970 paper. And it's just to take it with you in case you ever see it. This brings in yet another part of mathematics in this research, polyhedral surfaces, because Maxwell's theorem is about those graphs which are stressed, and the theorem says that they correspond to they are projections of a polyhedral structure. Okay? So our generalization, so the picture looks like this, right? So you have a polyhedral structure and it projects in the plane, and this graph has a stress, and we need the theorem to basically prove the expansiveness, because stress is dual to infinitesimal motions, and we use Farkas lemma from linear programming duality, so a lot of things that now I have to sweep under the rug. So let me conclude with the fact that we had to generalize this, and this generalization, I'm getting now to the reason why it was every other generalization to periodic was sort of doomed, because you had to do it with this exact definition that I gave you earlier. Otherwise, you don't get this type of theorem. Okay, so if you do it on a fixed torus, in other words, it will not work. So this is a periodic graph, and this is something that jumps at you like a 3D polyhedral structure. Yes, you see the cubes jumping at you. So in fact, it is a lifting of a periodic surface, polyhedral surface. So when we put everything together, we obtain this. So in dimension 2, now we have an infinite, unlimited possibilities for auxetic periodic designs via these periodic pseudo-triangulations. And in dimension 3 and higher, we have uncovered infinite families. And we'd like to have a characterization, but we cannot have the characterization prior to solving Maxwell's problem. And I'm going to stop here.